Hello everyone. In today's session, we'll be learning how exactly we can write an ARM code in order to count number of zeros and ones in an array of 32-bit numbers. Okay, that is, now here let's take this two examples shown here. Okay, we have the very first 32-bit data, okay, with 1 1 1 1 1 1 and 1 1. This is nothing but total 32-bit. Out of 32-bit, there are 8 ones, remaining 24 bits are zeros. Why am I telling something like that? We are finding the total number of ones and zeros which are present in the given array of data. Okay, in hexadecimal, which is nothing but 10 ones and 30 zeros. Okay, this is the final result that we want for this particular code. So let's see here. Okay, so because I have taken those two values, that is the answer. You can change the data here and see how exactly you are getting the output. Okay, let's see what's happening here. Okay, the very first term is area, that is an assembler directive which instructs to give a specific area or segment in the memory to store this particular information. This is a random name. Code is nothing but it instructs that the set of data or information is nothing but actual instructions. Read only, because we don't want any modification to be carried out on this particular code. Entry indicates where exactly the code starts. Start is a label. Okay, so here we have the very first instruction. Okay, if you see here, all these three values R2, R3, R7 are nothing but counters. Okay, we are using the register R2 in order to count the total number of zeros present in the given data, R3 to count total number of ones present, and R7 to actually give a count of how many total values are stored in the memory. Now in the memory we are storing 2 values, so it is 2. If we stored more values, it would be if there were 4 values, then it would be 4. Okay, a value is a label. Okay, and at this particular location we are storing all this particular data, so the address of value is loaded to R6. Okay, loop is again a label. Okay, now what is happening here is content of R6. Now because R6 points at value, the content that it will hold is this first value that is loaded into R0, okay, or R0, and then R6, whatever address is there which is initially pointing here, is incremented by 4 so that it points on the next location. The reason it is incremented by 4 is here we have used the term DCD, which means it is a defined constant double word, or in other words, the data stored here are 32-bit. Since each of 32-bit data occupies 4 memory location, in order to make sure the register R6 now points at the second location, we need to increment by 4. Next we have move R1, #32. This is again a counter, because this particular data, which is actually nothing but 32-bit data, okay, we want to make sure each bit is checked, so we use a counter for that, is R1, and that stores 32 as a value. Okay, you will get to know the usage of each counters in the next set of lines. So bit loop is again label. Okay, this is the most important instruction of this particular code. Here ROR is nothing but rotate right. Okay, and #1 indicates that rotate right by a value of 1. Okay, and R0 indicates the register name, okay, or the register whose content is to be rotated, and then the final result is stored back in R0. Okay, so what happens here is the very first value will take here. Okay, if this is our value, okay, if you rotate it right by 1 value, then what will happen is the last value here is rotated out and it is brought as the initial value, and everything here is shifted to right side. Okay, and one thing we should know here, every time the last value here it is shifted to the front, okay, because we are using move yes, which is setting conditional flag, this value which is moved, okay, its copy is stored in the carry flag. R0 content, let's assume the previous case, that is nothing but we have already copied our first value into R0, so this content is rotated by one value and the rotated content is now shifted to R0. Okay, and then we see a yes here. This is very important. If you just write move, you will not get the required data, because move s here, yes means set conditional flags. Okay, so every time we rotate it, we are setting the conditional flags. Okay, what this will do is nothing but whenever you rotate, the value which is rotated out, okay, that copy is stored in the carry flag. Okay, that is why this is also very important. Fine, we have addition being performed here. Okay, but if you check, we have a conditional code here which is carry set, which means that perform this particular addition only if carry is set. Okay, we already know in the previous step, okay, when rotation happens to the right side and the rightmost or the LSB bit is actually shifted out and it is moved to the MSB. When that happens, a copy of that is also stored in the carry flag, because we have set the conditional flags using move s. Then what happens is nothing but, if in case the moved value, the value shifted out from the LSB and moved to the MSB, if that value was 1, then carry flag would be set. If that value would be 0, carry flag would be 0. Okay, so here two addition operation is seen. If in case the carry flag is set or C flag equal to 1, this particular addition is carried out. If carry flag is 0, this particular addition is carried out, because this is nothing but carry set, this is nothing but carry clear. So based on which particular conditional code is true, that particular statement is executed. So let's consider the case wherein carry is set or C value is 1. In that particular case, R3 is incremented by 1. Okay, so that what will happen because of that? The counter R3, which is used to count the number of ones present, that will increment. But if in case that particular condition is not true, if carry is 0, this particular addition is carried out, R2 content is incremented by 1, because if it is not 1, it can only be 0. Okay, so this is how we are trying to count the total number of ones and zeros present. So next we can see, the label done, and what happens here is R1 is actually decremented by 1, so that we know if all 32 bits are checked. In our case, only first bit is checked, because of which there are still 31 more looping or iterations to be carried out. So we will branch back to the bit loop and this particular rotation continues. Once all 32 bits are checked and R3 and R2 registers are incremented accordingly, then what we have is nothing but we have R7 counter, which stores total number of data stored in the array. In our case, we have two values stored, so one particular R7 value is decremented here to indicate that we have already checked all 32 bits of the first data. Next, what we want to do is nothing but we want to take the next value, which is 0x22, because of which we will branch back to the loop, since R7 is not 0, because R7 is 2. Okay, first iteration is complete, means first data is checked. Now we want to check the next data, so we are branching back to loop, and here the procedure continues, because in R6 will be now pointing at the second value, which is copy it to R0 and whole procedure is repeated. Stop B stop is an infinite loop. We use that to prevent next statement, okay, or next line to be executed as an instruction. Okay, that's all. Fine. Now let's see how it works. Okay, so if you see here, let's start with the very first line, which is R2 is stored as 0, R3 is also stored as 0, okay, while R7 is stored at 2. Okay, now R6 points at the location or memory location where data is stored, and from our result here we know it is 38. Okay, and we can see all our data being stored in the memory here. Okay, next what we will do is we'll continue. Okay, so the very first data pointed by R6, which is 1111, is now copied to R0. Okay, as you can see here. Fine. Next, R1 is stored as 32, but 32 is in decimal. In hexadecimal it is 20. Then what we have is the next main part, that is nothing but move S R0, R0, rotate right by #1. Okay, so if you notice here, when 1111 is rotated once to right side, we will get the answer as 0x8888. Okay, why is that so? Okay, so these are the different values you'll keep seeing in the content of R0 for every rotation. Okay, that is because rotate right will shift all the contents towards the right side, and the last bit present here will be shifted to the initial position. Okay, same procedure continues, that is shift to the right, last value in the first position. That's what you see here, shift to the right, last value in the first position. Its hexadecimal value is shown here. Okay, and every time the last bit is rotated and brought to the first position, okay, a copy of that is stored in carry flag. Okay, next we have to perform addition if a carry is generated. Let's see what is happening here. After this first rotation, we can see is carry value is actually equal to 1. Okay, because of which instruction should be executed? Carry conditional code carry set or carry clear. Among this, carry set conditional code will become true if in case C value is 1, because of which this particular instruction is executed. Okay, and the next instruction is ignored. Okay, so now one iteration is completed, and you will branch back to bit loop. As you can see here, in this round R3 was incremented, because of which R3 value is 1 here. Okay, in the next round what will happen? If it is 8888, the last bit is actually 0. Okay, because the last bit or LSB is 0, after this particular rotation, okay, what will happen is nothing but carry set will actually be false, carry clear will be true, because carry flag will be actually equal to 0. Okay, and because of that, instead of R3, this particular statement will be ignored and this will be executed. Okay, so you can see R2 is now incremented. Now we'll continue this. Now we have finished executing and checking all the bits of the very first value, and we got the answer in R2 and R3 as 8 and 18. So there are 8 ones and 18, which is nothing but decimal value 24, 18 in hexadecimal as number of zeros. Now the code will continue. Okay, and what will happen here is R7 is decremented by 1, that we know one more value is pending, because of which it is R7 is not 0 and will branch back to loop. okay, so that the next value is considered. Okay, again the procedure continues. As you can see, R1 is now 1. It means one iteration is pending, okay, out of the 32 bits. One more bit is there to check, okay, and now all bits are checked. As you can see, R3 is now 10, R2 is 30, which is nothing but 16. 10 is nothing but 16 in decimal, 30 in hexadecimal is nothing but 48 in decimal. Okay, as expected, we are getting the same number of ones and zeros, okay, from our code. That's all.